Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today we would like to do some problem regarding dielectric medium. So what we are doing today is supposed to be a tutorial sessions, and then we're going to focus on the problems taken from our textbook, which is Sadiku textbook. And then the problem number that we're going to solve together will be as shown here, which are problem 5.26, 5.30, 5.39, and 5.41. So that should be our objective in today's tutorial session. So we're going to do problem 5.26 now. So I'm going to show you the problem. So we're going to read together, and then from there we're going to solve together the problem. So I'm going to show you now problem 5.26. Okay, hope you can see the problem. Okay, 5.26. Okay, so the problem will be shown here. I'm going to indicate with my blue ink now. So that should be our intention for this particular session. Okay, so what's given here is consider figure 5.20. So figure 5.20 is this one, which is a spherical dielectric shell. So what we have now, we have a material information given. Before, if not mistaken, we have done the same, quite a similar problem before, but we never take into consideration the medium, the material part. But in this problem, so it's specifically inform us about this dielectric shell is made of, this spherical shell is made of dielectric material. Okay, so when you're given a dielectric material, the parameter that should be looked for is known as epsilon, which is known as permittivity. And in this particular definition, the permittivity is given as epsilon naught epsilon r, where the epsilon r here is known as dielectric constant or relative permittivity. Okay, so meaning that this spherical shell is made of dielectric material, and other than that, meaning that the region inside the shell and outside the shell is assumed or is stated to be free space. Okay, so what's given now in this problem? If a point charge Q is placed at the center of the shell, so meaning that we are going to place a point charge at the center of the shell. So the question asks us to find P. So what should be the name given for the symbol capital P here? Okay, so we should know P is known as polarization vector. For the B, the question asks find rho VB in the region between R greater than A, R smaller than B. So meaning rho VB here is known as bound volume charge density. And for the third part, the question asks us to determine what are the surface bound charge at the surface of R equal to A and R equal to B. So there are three items that we need to solve. First, the polarization vector. Second, the bounded volume charge density. Third, the bounded surface charge density. So that's what we're going to do now. Okay, so let's do it. Okay, so let's draw our problem now. So we're going to draw our problem. So 5.26. So what we have a spherical shell. So I'm going to draw our shell. So this should be the inner surface of our shell. This is the outer surface of our shell. The radius given as A, and then the outer radius given as B. And then the medium, meaning that this region between A and B is filled with dielectric material where permittivity is given as epsilon naught epsilon R. Okay, that's what define our permittivity of the dielectric material. Okay, so then the question states, when we place a point charge Q here, so therefore we are putting a point charge at the center of the shell. So for the first part, the question wants us to determine A, what is the polarization P, okay, in the region of A smaller than R smaller than B. So that should be the first part of the question that we need to solve. Okay, so let's talk about this problem now. Okay, since we are placing a point charge here, so now this point charge is going to emit what we known as electric field. And then we know in terms of electric field, you can represent either in electric field intensity or electric field density. So that's what we need to find now. What are the electric field coming out from the point charge? Because that should be the source of the field in this problem. And from charge to find E, we need to use either Coulomb's law or Gauss law. So in this case, I'm going to use Gauss law because as far as method is concerned, Gauss law is much easier to be used rather than Coulomb's law. So therefore, I'm going to find D, okay, using Gauss law. That's what I'm going to do. I'm going to put in terms of statement here. So therefore, with Gauss law, I can see the approach here to label the region concerned. So I can see in this problem, there are three different regions that I can determine the E. So I'm going to denote the region as region number 1, region number 2, and region number 3. Okay, so now I'm going to find three different regions of field. So I'm going to state now region number 1, which is constant for R smaller than A. That should be our region number 1. Region number 2, which is A smaller than R smaller than B. That should be our region number 2. And for region number 3, so as you can see from our diagram, should be R greater than B. Okay, that should be three distinct regions of interest. Then for region number 1, I know that in terms of Gauss law, D dot ds equal to Q enclosed. Okay, so what we have to do, we have to build a Gaussian profile structure here. And then from our previous experience, we know that the left-hand side should be equal to dr 4 pi r square. And then the Q enclosed should be Q. Therefore, in terms of D1, should be equal to Q divided with 4 pi r square in r direction. Okay, that should be our D1. And for D2, it's going to be the same. If you repeat the same method, building the Gaussian profile, solve the mathematics of Gauss law, you're going to end with the same solution. 4 pi r square in r direction. Similarly, for region number 3, is going to be the same. D3 is going to be equal to Q divided with 4 pi r square in r direction. Okay, that's done. That's finding the D. So next we need to find the E. Okay, so generally what we are saying, the relationship between D and E is given by this simple formula. Okay, I'm going to put the relationships between E field and D fields. Okay, is given by D equal to epsilon E. So that should be our standard definitions. Okay, therefore for region number 1, what we're going to have, so E equal to D, okay, E1 now, region number 1, should be D1 divided with the epsilon medium. Okay, because E equal to D divided by epsilon, but what is the medium concerned in region number 1? As given by the question, should be free space, therefore should be epsilon naught. Okay, therefore for region number 1, the solution should be Q divided with 4 pi epsilon naught r square in all directions. Okay, how about region number 2? For region number 2, since the medium now is a dielectric, okay, therefore the epsilon here should be epsilon naught epsilon r. So what we're going to state now for E2 should be D2 Q divided by 4 pi. Remember the medium now is epsilon naught epsilon r r square in r directions. And for region number 3, we know it is a free space as well. So the solution for the field in region number 3 is exactly the same as the field in region number 1. So for E3 now, should be equal to Q divided with 4 pi epsilon naught r square in r directions. Okay, so now we have able to determine the D fields and the E field. So why is important to find the D and the E? Because that is very significant when we want to find the P. So why? So let's state the reason now. Okay, the P actually is denoted as, remember the equation we derived together in our previous lecture? D minus epsilon naught E. Regardless any medium, either is dielectric or free space, the constant here must be epsilon naught. It's not epsilon, okay? Must be epsilon naught regardless any medium that we need to solve, because that is standard formula. Okay, that is what we have to know. Okay, so now the question asks for region number 2. I'm going to focus for region number 2 only. So for region number 1, I know that the polarization should be equal to 0. Okay, because as you can see, if I substitute the formula D1 and E1, the final solution should be 0. Similarly, for region number 3, the result for polarization vector also should be equal to 0 as the same reason stated before. But for region number 2, there's going to be a value. So let's substitute now. Yeah? So let's do it now. Okay, for P, I'm going to put P2 now. Okay, that should be our region number 2, should be D2 minus epsilon naught E2. Okay, that should be the standard formula we should use. Epsilon naught remain as it is, so D2 due to the P2, E2 due to the P2. So now when we substitute, so you just need to substitute D2 with this substitute. So I'm going to have Q over 4 pi, okay, so r square, and then I'm going to minus, okay, r direction, don't forget what direction, so it's a vector, P is a vector, so how about epsilon naught? So put epsilon naught here, and then E2 should be this one, Q over 4 pi epsilon naught epsilon r square in r direction. So what we can do, we can simplify the mathematics. by cancelling the epsilon naught, epsilon naught. Okay, so when we do that, you're going to have final solution Q over 4 pi r square, and then I can open bracket 1 minus 1 over epsilon r. In which directions? R direction. What should be the unit? Should be coulomb per meters. So that should be the solution for the part A. Okay, finding polarization vector. So as shown here, we need to find the D and we need to find the E. So how to find the D and the E from the charge? By utilizing either Coulomb's law or Gauss law. Yeah? So as you can see, even though we are in the week number 6, yet we still have to use knowledge based on the week number 2 or number 3. So therefore, that's why EMT is interrelated in terms of topics. Okay, that's done. So the question number 2 said find rho VB. So I'm going to rewrite what the B. So number 2 said find rho VB in region number 2. Okay, where is A smaller than R, smaller than P. So how we able to do this then? Yes, using the information that we seen before, the formula that we have been shown, which is, okay, rho VB. Okay, I'm using standard formula rho VB equal to negative divergence of P. So as you can see, without knowing the P, we cannot find rho VB. In order to solve for rho VB, it's very important for us to know the polarization vector. So if you have wrong solution for the P, therefore we have wrong answer for the rho VB. Okay, so that's why it's very important in terms of accuracy. You must make sure your working solution accurate and without any error, because the error going to be migrate to the next solution you're going to solve later on. Okay, so let's do it. So standard procedure again. So what this equation is known as? So this equation is known as divergence. Okay, so usually you will given a divergence table. So for those who have taught the textbook, you can refer to, as I'm referring now to my textbook, page 79. And then I can see there are 3 equations of interest. So we're going to focus to equation 3.31. So let's do it. Okay, so if you refer to that equation, the equation state that divergence of P, I'm just copying the equation now, nothing extraordinary, just copying. Hopefully my eye still okay. 1 over R square, that should be the table, D over the R, bracket R square, P component R. Okay, that should be the first term I can see from the table, plus 1 over R square, R sine theta, D over D theta, open bracket, P theta sine theta. Okay, that should be the second term from the table. And for the third term, should be 1 over R sine theta as well. But now we are dealing with the phi component, D over D phi, P phi. Okay? So that's extracted from the table of equation 3.31 from page 79. So let's solve the problem. So from the above P solution that we solved together, we can see that this particular magnitude is only based on one variable, which is the R variable. So therefore, what we can say, this is known as PR component. And in other words, what we can conclude for the P theta component is equal to 0 because we don't see any theta terms equation here. Similarly, for the P phi component also is equal to 0 because we can't see any phi component in terms of the phi solution that we solved above. So therefore, I'm going to put 0 here. Then I'm going to put 0 as well here. So we end with 0. But yet here, this particular PR, I'm going to substitute with Q over 4 pi r square. And then I'm going to put 1 minus 1 over epsilon r. I'm going to ignore the directions because what we need to substitute in this particular term is only the magnitude. No direction should be included, only the magnitude. So let's solve the mathematics. Now I can see there's r square here. And then this r square here. So everything inside this bracket is a constant. Therefore, the solution of the divergence of rho v, divergence of P is equal to 0. Therefore, what we are saying, this is equal to rho VB. So rho VB is equal to 0 in region number 2, which is within the dielectric shell. Okay, that's done already. Okay, so now let's proceed to the third part. Okay, I'm going to turn over. Okay, for the third part of the questions, it requires us to find rho SB. Okay, so now for number C, the question asks us, what is rho SB? Okay, at R equal to A and R equal to B. Okay, that should be two solutions that we need to solve. One at the surface of R equal to A, and the second solution refer to the surface of R equal to B. So let's focus on the R equal to A first. So let's say I'm going to find solution. What should be the bounded surface charge at the surface R equal to A? Okay, that should be my interest now. Usually for this particular problem, I like to draw a diagram to help me in solving the problem. So that's part of the surface. So I'm going to say this is region 1, which is our free space. This is region 2, which is our dielectric. And from the solution that we solved before, the polarization vector only exists in the dielectric. So what we state before, there's a P here. Okay, this is our P2. Is there any polarization vector in the region number 1? The answer is no, because free space. The only polarization vector that appear to be at this particular condition or situation is in the region number 2, and the direction of our P is as shown in the R directions. Right? So now I'm going to find rho SB. What should be rho SB here? Okay, what should be our rho SB located here? Let's denote that now. Rho SB. What should be rho SB at this particular surface? So therefore, the way we have to do it, we have to refer back to our discussion before, where we determine rho SB using formula given as rho SB equal to P dot AN. Remember that formula? Okay, P is the polarization vector. AN is the unit vector. Okay, so now what you have to see now, you have to define now unit vector. In this case, unit vector can be defined either red direction, so this is one unit vector AN, or you can define the unit vector to be in these directions, AN. Because both are unit vector, both are normal to the boundary. So which should be the one I'm going to take in this substitution? The red AN or the blue AN? Okay, So the way we define the AN, always using this principle. Unit vector is the direction of vector, okay, direction of AN showing away from the dielectric that contains P vector. Okay, again I'm repeating, AN is selected based on this definition. The direction of a unit vector must be in the direction showing away from the dielectric medium that contain the polarization vector. So in this particular diagram, the region of dielectric contain the polarization vector is this particular region. Therefore, the unit vector that I'm going to choose for this substitution going to be this one. Why? It's showing away from the dielectric that contain the polarization vector. That is very important, because when you deal with a condition where there are two dielectric, both dielectric going to produce their own polarization vector. So the way you are choosing the unit vector by choosing a direction away from the dielectric of the P that you are calculating. Okay, so let's substitute now. So what should be rho SB? I'm going to put R equal to A now. Okay, let's do it. So what should be our PQ over 4 pi, and then I'm going to put R equal to A squared, 1 minus 1 over epsilon R, should be in R directions. Okay, that's R direction. Dot with AN. So AN is away, is opposite to this direction. So it's going to be negative R. Okay, so therefore the solution going to be a negative charge. Negative Q over 4 pi A squared, 1 over epsilon R coulomb per meter squared. That should be our solutions. It's very important for you to be particular about how you choose the unit vector of AN directions. That's what you have to see in this particular problem. Okay, so let's repeat our understanding, now focusing on the other surface. So maybe you can stop the video and try to solve first the problem yourself, then you can compare with my method shown here. So just, it's up to you. If you feel you want to try your understanding, you can do it before you see my solution here. Okay, now I'm going to do for R equal to B now. Okay, so now I'm going to repeat. The boundary of interest is going to be shown, but now we are focusing on region number 2 and region number 3. And then the way we're going to draw the polarized vector in the region number 2. So that should be our P2. Okay, there's no polarization in region number 3 because we know region number 3 is filled with free space. Now let's find the rho SB here. I'm going to straight away substitute now. So rho SB, R equal to B, should be Q divided by 4 pi B squared, because R now need to be substituted with B, 1 minus 1 over epsilon R in R direction, because direction still in this particular symbol, dot with now AN is away, so now this should be our AN, okay, away from the dielectric that contain our P, so should be R. Now we have the solution as positive volume surface, sorry, positive bounded surface charge, 4 pi B squared, 1 or minus 1 over epsilon R coulomb per meter squared. That should be our solution for R equal to B. What should be the bounded surface charge density at that particular surface? Alhamdulillah, we have solved problem 5.26. Okay, taken from our Sadiku textbook. Okay, now let's proceed to problem 5.30 now. Okay, so 5.30 is our concern now. Okay, so 5.30, I hope you can see the problem here. Okay, so I think I'm going to indicate again using my blue pen here. So that's 5.30. Again, the problem is regarding the usage of medium, usage of material in the problem. It's quite similar to the problem we have seen before when we talk about potential, but now the only difference here, material is included in our problem statement. So that's the only difference. So let's look into it. A solid sphere. So you have now not a spherical sphere before, now a solid sphere, meaning that is a ball, it's a golf ball problem of radius A and dielectric constant epsilon r. So it's not permittivity is given here, is a dielectric constant. It's totally different than before. Has a uniform volume charge density rho v. So now the question wants us to do for part A, prove that at the center of the sphere, the potential is given by this equation. Okay, so let's copy the equation. You better copy the equation because we need to prove this equation to be the solution of our end product later on. And then for the B, find the potential at the surface of the sphere. Okay, so that should be our problem now. Right? So, (5.30). Okay, now given here a solid sphere. Solid sphere. Radius A. And the charge given in this problem is known as volume charge, located in the region R smaller than A. Okay, that should be, so now what we need to, for part A, prove V at the origin is equal to rho naught A squared over 6 epsilon naught R squared. I have to see the formula properly. Sorry. Okay, 6 epsilon naught epsilon R, 6 epsilon naught epsilon R, and then 2 epsilon R plus 1. Okay, so let's state here again. Can you see the formula here? Okay, rho naught A squared over 6 epsilon naught epsilon R, 2 epsilon R plus 1. Okay. So now the rho V here is given as rho naught. Okay, that's the statement of rho V is equal to rho naught, it's constant here. Okay, so how we solve this problem? Okay, so as you can see, it's given charge. We need to find the V. And we have to ask again, what should be our V here? Is it potential? Is it absolute potential? Yes, because we are referring at the point here, the origin. So this is our origin, okay? So what should be the V here? And then since the point here is only one point, Therefore, I'm going to state now the V is known as absolute potential. So I'm going to state now the V here is defined as absolute potential. So therefore, I'm going to write here, this V is known as absolute potentials. Okay, so when you talk about absolute potentials, the reference is going to be assumed to be infinity. So therefore, we're going to state here, assume our reference is at infinity. Okay, that's what my statement now, because I'm saying the V is absolute potential. Therefore, the reference for my definition of absolute potential is at infinity, because this is our end position. The initial position will be at infinity. Okay, therefore, in terms of mathematics, I'm going to say now V is going to be equal to minus, okay, E dot dl, that should be infinity, and this should be the final destination. And that's how we define absolute potential, standard formula. So now I need to find the E. Okay, so to find the E, what needed now? The source. So given the source rho V, so the E can be determined using Gauss law. So I'm going to put now E is determined by using Gauss law. Okay, that's what we are going to continue using Gauss law. So Gauss law, what we need to know, we have to label the region properly. So I can see there are two distinct regions, region number 1, which is R smaller than A, and region number 2, which is R greater than A. So therefore I have two regions here. Okay, region number 1, which is R smaller than A, and region number 2, which is R greater than A. Okay, that should be my two regions of interest. So now I'm going to focus for region number 1. So I know that by placing my Gaussian to be as shown in this my movement of hand here, so I can say d dot ds equal to q enclosed, and then I know that from my previous solution, the surface of a sphere should be 4 pi r square, and then now we have a volume charge, okay, rho v dv. So I'm going to put rho v dv should be r square sine theta dr d theta d phi. Okay, so triple integrations r from 0 to r, theta 0 to pi, phi 0 to 2 pi. So when I solve the mathematics, inshallah, you're going to have rho v 4 over 3 pi r cubed. That should be the solution for the integration. And you can see the limit of my r from 0 to r, because now the Gaussian is as shown dotted line here. So this is our r. So for the region of where the charge need to be calculated in the region less than r, from 0 to r. That's where the charge actually been considered in this calculation. Even though we know that there's still charge exists in the region from r up to a, but based on the definition of Gauss law, the charge that we need to consider in the calculation are only the charges that contain within the Gaussian profile. So now our D1 should be equal to, what we can do, we can cancel the 4 and the pi. So rho v r over 3 in all directions. Okay, so I'm going to put rho naught now, because what we have, rho naught r over 3 in all directions. That should be for D1. Okay, if you repeat for D2, so you're going to do the same thing here. Okay, I'm going to just solve now. dr, okay, 4 pi r square for the left hand side of the Gauss Law equation. But now when I do the integration now, triple integrations, rho v r squared sine theta dr d theta d phi. Okay, yet the limit for my r now should be from where to where? R. Because now my Gaussian is located here. So what should be my limit of the r enclosed by the outside Gaussian? Good, from 0 up to a. Now you can see the difference. Before 0 up to r, now you have to change the limit of r from 0 to a to take into account all the charge contained by that particular outside Gaussian. Other than that, remain the same, 0 to pi for theta, 0 to 2 pi for phi, and the solution here going to be rho v, rho naught, 4 over 3 pi a cube. Okay, here for r cube, now a cube. So now let's simplify the mathematics. For D region 2, should be rho naught, 4 we can cancel, pi we can cancel, should be a cube over 3 r squared. In which direction? R directions. Okay, so but it's not our end product yet. We need to find not the D, we need to find the E, because the equation that we need to substitute to find the V is not D but is E. So now what we have to do, we have to convert the D to the E. Okay, so using standard formula again, D equal to epsilon E. Remember that? So now what we can conclude now, that E1, okay, remember, E1 in the region where contain the dielectric, so dielectric given here, epsilon R, okay, the question given by the problem, I mean, the information given the problem, the dielectric is having dielectric constant epsilon R, okay, that should be the epsilon R. Okay, for E1 should be what now? E d over epsilon, so rho naught, R over 3 epsilon naught epsilon R in R direction. That should be E1, because the medium here is dielectric. So we need to substitute the epsilon here with epsilon naught epsilon R, because what given in this particular question, the information of dielectric constant epsilon R. So we have to make it proper by multiplying the dielectric constant with epsilon naught. Therefore, what you have should be like this. And for region number 2, E2, because the medium now free space, should be rho naught a cube over 3 epsilon naught r square in r directions. Okay, that's done. So now let's go back to our objective here to find V. So now I'm going to set this is equation 1. Okay, so let's continue. I think we still have space here. Okay, from equation 1, okay, now the V that we need to find now, V is located where? Here. So now my initial location is infinity. I have to move from infinity to the final destination. Okay, so I'm moving now from infinity location, I'm moving to the final destination. I can see there are two distinct regions, region number 2 of E and region number 1 of E. Okay, so I can see in terms of mathematics, minus from infinity to A, I can see the E here should be E2 dot with DL. Okay, so what I'm doing now, just moving from infinity to this position A. So this is where I have gone through so far based on the mathematics, but yet I have to continue. So I'm moving further into the spherical structure. Now from A to the origin, E1 dot DL. Okay, so this interpretation based on our diagram. Infinity to A, E2, A to 0, E1. Infinity to A, E2, A to 0, E1. So now let's substitute. So what we're going to have now should be equal to, okay, minus E2. Okay, rho naught I'm going to take out. A cube over 3 epsilon naught, that should be our constant. I'm going to integrate, what is it to be, 1 over r square dr. Okay, and then the limit integration should be infinity up to A. Then I'm going to continue, minus, so E1 now, rho naught over 3 epsilon naught epsilon r. I'm going to integrate now r dr. From where to where? A to 0. Okay, so that's what after substitution. So what we're going to have here, so this particular integration will give us a minus 1 over r, correct? And this integration will give us r square over 2. Okay, so now what should be our solution now? Equal to, okay, so I'm going to put negative, negative gone already. So I'm going to say should be rho naught A cube over 3 epsilon naught. Then the final solution here should be 1 over A. Okay? And then minus rho naught over 3 epsilon naught epsilon r. Okay, bracket. So now 0, 0. So minus, so should be minus A squared over 2. Okay, so when you substitute now, so A squared becoming plus. Okay, so let's take out, and then I can cancel the A here. So let's cancel this becoming 2. I can cancel this one, that's okay. And then now becoming plus. So let's make it similar to the one that we been asked to solve now. Rho naught A squared over 6 epsilon naught epsilon r. Okay, let's do it now. So now I'm going to put here, so 6, I have to do what? Yes, I have to put 2 epsilon r and then plus with 1. So Q, E, T. Okay, so that's done. Alhamdulillah. So we have solved the problem. So I'm sure for part B, you can prove yourself based on the equation 1 here. But since the question wants us to find the potential on the surface of the shell, or sorry, the surface of the sphere, so therefore we just need to do the integration of E from infinity to A. So that is answering the question, what should be the potential on the surface of the sphere? Yeah? So you just do this part, then inshallah you're going to get the solution asked by Sadiko. Okay, so with that, we have completed for problem number 2 that we are targeting in this tutorial session, problem number 2. Okay, that's done already. Okay, so let's continue now for different type of problem, but yet still utilizing dielectric medium. Problem 5.39. So let's do this problem, 5.39. Okay, 5.39. Okay, so this is supposed to be this problem now. Hope you can see the question, 5.39. Sorry about my table lamp is getting dimmer now, maybe due to the battery. So, but it's okay, hopefully you can still see it. Okay, so what given here, a plane Z equal to 0 separates region 1, defined as Z greater than 0, which is a dielectric material with epsilon r equal to 4. From region number 2, r smaller than 0, which also a dielectric material with epsilon r equal to 6.5. If given D1 is equal to 16x plus 30y minus 20z nanocoulomb per meter squared, find P1 and D2. Okay, so therefore let's redraw problem 5.39. Okay, we are doing this one. Okay. Okay, 5.39. So I'm going to draw the boundary as shown in my lecture, flat like this. Okay, so region number 1. So this boundary is given by definition Z equal to 0. So defined by the question, Z greater than 0 is defined by region number 1. And then for region number 1, the dielectric constant epsilon r is given equal to 4. And for region number below region number 2 is defined by Z smaller than 0. So therefore, this is our region number 2. And then epsilon R2 is given by the question 6.5. Okay, this should be defined by epsilon R1 to differentiate the relative permittivity of two different dielectric materials. So given by the question again, D is located in which region? Good, in region number 1. So given by the question, there's a D. And the D given by the question is D in region number 1. Where D1 is equal to 16x plus 30y minus 20z. Unit-wise, nanocoulomb per meter squared. Okay, so that should be D1. Now the question wants us first, what is P1? Okay, number 1, determine P1. So we have to know now P1 is known as polarization vector. And then P1 here, we know should be equal to D1 minus epsilon naught E1. Okay, where we can write now E1 equal to epsilon 1 D1. Sorry, D equal to epsilon E, sorry. So D1 equal to epsilon E1. Okay, that should be the correct version. Okay, so therefore what we need to find, since given here is D, we need to find for the E. So what we can say, E1 should be equal to D1 divided with epsilon 1. And epsilon 1, as what we already know, should be defined as epsilon R1 epsilon naught. Okay, so therefore you need to find that and then you substitute into the equation. So what you need to do, D1 is just using the given solutions. For E1, you need to find from the D1 using these particular terms, and then substitute everything there, and then you can solve for P1. That should be the method to find the P. Okay, and then for question number 2, the question asks us to find D2. Okay, so now in the other region. So what we are given by the question, the field in region number 1. And then the question wants us to solve what should be the corresponding field in region number 2. Okay, so in order for us to find D2, we need to use the information of D1. Okay, so now the D1, okay, so what we have to use method-wise, using the boundary condition. What I'm going to say now, since the question gives us D1, so we need to find D2. So that should be what been asked by the question. That should be the intention. Given D1, need to find D2. So what we have to do in order to achieve this particular objective, we need to use what's known as boundary conditions. Okay? So what you mean by that one, remember when we talk about D1, it can be split into two components, consists of D1n. Remember, D1n is referred to be normal component of the D1 plus with the D1t. Okay, D1t known as the tangential component, because D1 actually can be re-equate as D1n plus D1t. D1n, D1t. Remember that method? So this is our D1t. This is our D1n. So by saying D1 equal to D1n plus D1t, so we're actually splitting the D1 into normal component to the boundary and tangential component to the boundary. And we know that D2 also consists of D2n plus D2t. So what we need to do to find D2 is not straightforward. What we have to do first, we need to relate D1n to D2n. That should be our first task. Boundary condition number 1. What does it say? Our normal component. Remember the one that we proved together? D1n minus D2n equal to rho s. Okay, that should be the first task that we need to do. Then what we have to do, we have to relate the tangential component of D1 to the tangential component of D2. So how we do it? Using boundary condition number 2, or we call it to be tangential component. With the equation y, E1t should be equal to E2t. So that should be what needed to be done here. It's not simply saying this method. You need to split first, then you need to do the individual boundary condition equation first, the normal, and then you have to repeat again using the tangential, and then the D2 actually equal to what? D2n plus D2t. So that should be the method that you need to do or to use. Okay, so you want me to do it for you now, or you think you want to try it yourself? Okay, so I think some of you said you want me to show you. Okay, let's do it now. Sorry about the brightness of the lamp here is getting darker now. Even my eyesight now getting blurred. Okay, so let's do it now. What I'm doing, I'm going to focus on splitting D1 to D1N plus D1T. So that's what our objective now. Okay, what we're going to do now, we are saying D1 equal to D1N vector plus D1T vector. That's what we're going to do. We intentionally going to split this D1 into two terms. Okay, now I'm going to focus on normal component of D1. Okay, so therefore, what is it? This should be known as D1N vector. And in terms of variable, I'm going to say is equal to magnitude D1N, direction AN. That should be the equation representing my D1N. So how do I define the AN? Normal to the boundary. What I mean by normal to the boundary? Yeah, this is what AN should be. AN. Okay, AN should be unit vector normal to the boundary. So therefore, this AN, in terms of diagram, should be represented by these unit vector directions. Okay, so from the diagram, okay, above, what we can conclude, AN is equal to what? What is the equation of the boundary? This equation correct? So you have z equal to 0 plane. What should be the unit vector to that plane? Good. Should be equal to z. Okay? Because that should be related because the unit vector is normal to the boundary. The boundary is given by z equal to 0. Therefore, the AN must come from this expression. So by definition, the unit vector normal to z equal to 0 is z. So that's done. Now I want to find the magnitude then. So now what should be D1N? Magnitude D1N now. I want to find for D1N. What is D1N? Remember, this is my D1N. So how do you find D1N? Good. Just doing this mathematics. D1 vector dot with AN. That should be the formula you use to find the magnitude of D1. What is the D1? D1 is given by the question. Should be equal to 16x plus 30y minus 20z. I'm ignoring the nano here, okay, because I know that everything nano coulomb per meter squared. And then I'm going to dot with what should be my unit vector now, AN, good, z. So now if I dot it, what should be my final solution of the magnitude? It's going to be negative 20. Okay, actually nano coulomb per meter squared. That should be my magnitude of D1N. So what is vector D1N? Oh, sorry. So now finally, we are saying D1N vector is equal to the magnitude multiplied with the direction should be minus 20 z directions nano coulomb per meter squared. So we have completed with the task to extract the normal component from D1. Okay, please repeat this method when you want to extract the normal component for the given field. Okay, so once we obtain the D1N, we want to determine D2N. Okay, so the D2N can be found from D1N using boundary condition number 1. Yeah? But since the problem here, there is no surface charge density, therefore rho s is equal to 0. So I'm going to write it nicely now. Since rho s equal to 0, therefore what we're going to say D2N vector is equal to D1N vector. Okay, so alhamdulillah we have completed part number 1. So this term has been found. So now what we need to do, we need to find what should be d to t. Okay, so to get d to t, we need to extract from d1t. So how to obtain d1t from d1? Okay, that's what we're going to continue now. I'm going to use the available space here. So now my second part, tangential component. So I want to find d1t. How do I find d1t now? Okay, using this equation. So d1t equal to d1 minus d1n. Agreed? d1t equal to d1 minus d1n. So d1n we know already equal to minus 20. So when we put into the equation, should be equal to 16x plus 30 y nanocoulomb per meter squared. So alhamdulillah, we are able to find the solution for d1t. But yet if you refer to the boundary condition number 2, what needed here to equate the field in region number 1 equal to region number 2 is not d. We must use the e term. Therefore, you have to convert now the d to become the e. So now, what should be our E1 t? Okay, d equal to epsilon e. E should be equal to d divided with epsilon. So now should be equal to d1t that we obtain up here divided with epsilon 1. What is epsilon 1 equal to? Good. Should be epsilon r1 epsilon naught. That should be E1t. And then using boundary condition number 2, so what we are saying now, E to t is equal to E1t. Okay, therefore E to t now is equal to d1t over epsilon r1 epsilon naught. Okay, so therefore done already. So now what we need to do, we have to find d to t, and d to t now equal to epsilon r2 epsilon naught multiply with e to t. Okay, what's e to t? So therefore I'm going to write slowly now, should be epsilon r2 over epsilon r1 should be d1t. Okay, so what's d1t? This term, put in here, what is er2? 615, er1 4, then you're going to get the d2. So what should be the final solution here? The d1n equation number 1 and d2t equation number 2. You need to sum together in order to get the solutions. Okay, so that's how you should continue. Sorry about I'm going to show you the method. Again, repeating. For d1 need to be splitted into 2 components. Then the normal need to be related to the normal using the boundary condition number 1. The tangential need to be related to the tangential using boundary condition number 2. So what you need to first able to do, need to be able to define the normal component and tangential component of the given field. Then how you determine that d1 normal component? By using this method. Look at the method carefully. Once you're able to extract the normal component, then you can find the corresponding normal component using equation number 1. And you can see, since the problem there's no surface charge, we are assuming the rho s equal to 0, therefore d1n equal to d2n. So therefore we are saying that one. Therefore that should be in our equation number 1. Then to find the tangential component using the initial equation, since we already know the normal component, you'll be able to find the tangential. But yet, when you want to relate to the corresponding tangential, you have to use the E term. So the D need to be converted to the E using standard formula D equal to epsilon E. Then we know that the E to T is equal to E1T. So the question asks for the D2, you need to convert the E to the D again. Then from there, term number 1, normal, you add to term number 2, tangential, you're going to get the solutions. Okay, so I think I have to stop here. Unfortunately, I cannot solve the last problem as promised, but I'm sure you can give a try. But anyway, if you still can't do it, you can give a shout to me. Then I'm going to redo it in my other video sessions. With that, sorry about the technical mishap. So I'm sure you can understand with the current situation we are in now. So we have to help each other to get through this problem time. So no point is blaming each other. So just think positively. So with the limitation that we have, we still need to continue with our life. So thank you very much for your attention. Inshallah, we're going to see each other in our future video. Assalamu alaikum wa rahmatullahi wa barakatuh.